Hi class! Today we'll discuss differential leveling with and without turning points. The instruments that we'll use are the leveling rod. The one that we'll use looks like this, but there are other variations for the leveling rod. We'll also use the precise level, also known as the dumpy level or automatic level, chalk or marking pins, and plumb bobs. For the first step, the professor designates the locations of 2 points A and B, which can be observed from a single instrument setup and of considerable difference in elevation. Next, set up the level on a suitable point, preferably equidistant from the assigned points A and B. Adjust the height of the level to be convenient for the instrument man by using the leg screw of the tripod. Make sure that the base plate of the level is nearly parallel to the horizon. To do this, locate the bubble on your instrument. The location may differ from model to model. Then rotate the screws at the bottom until the bubble is at the center. Afterwards, rotate the precise level clockwise or counterclockwise in its base. If you level the instrument correctly, the bubble should stay at the center. Next, position the rod man at point A. The rod man should hold the leveling rod vertically with the help of a plumb bob. Afterwards, the instrument man may now take the backside or BS of point A. The reading must be done up to an accuracy of a millimeter. The recorder will simultaneously write down the measurements in a preliminary datasheet. So when you look at the precise level, what you see is something like this. If the vision is blurry, you must rotate the screw on the side of the precise level until the image becomes clear. Once clear, you may now take the measurement. So to read the leveling rod, one must know the meaning of each marking. First of all, the leveling rod is sectioned by equal intervals, and each section is equivalent to 10 centimeters. The markings on the right indicate 1 centimeter, while the markings on the left indicate 5 millimeters as shown. So if you look again through the instrument, just identify where the crosshair hits the leveling rod. In this case, it hits a little above the 189 centimeter mark, but below the 5 millimeter line. So you can just estimate this measurement. We estimate it as 189.1 centimeter. Once again, the recorder should write this down. Next, rotate the telescope until point B is in sight. The rod man must now transfer the leveling rod at B as well. Take the foresight or FS reading of the leveling rod by doing the same thing we did earlier. So when we look at the scope, this is what we see. Using the crosshair as reference, read the leveling rod. In this case, it's a bit above 44, but below the 5 millimeter mark, so once again, just estimate this point. So we estimated it as 44.2 centimeter. And the recorder will write this down in the preliminary datasheet as foresight at B. Afterwards, move the precise level to a new location and repeat the entire procedure for trial 2. Now, using station B for our backside and station A for our foresight. Now, you might be wondering why the previous level was white while this latest one is yellow. The reason is because the previous measurement was more than 100 centimeters. This leveling rod is colored in such a way that your 0 to 100 centimeter marks are yellow, 100 to 200 centimeters are white, 200 to 300 centimeters are yellow again, and it continues this pattern until you reach 500 centimeters. Now, the final step for this part of the fieldwork is to compute for the needed values. Looking at our sample preliminary datasheet, we'll use the recorded backside and foresight of stations A and B to get the difference in elevation. So for trial 1, these values are 189.1 cm for backside and 44.2 cm for foresight. To get the difference in elevation, it's just getting the absolute value of the difference between the foresight and the backside. Looking at this figure, you'll see how that gets the difference in elevation. Backside and foresight is just the height from the ground to the line of sight of the instrument. As you can see, the higher the value, the lower its elevation. So solving for the difference, we get 144.9 centimeters. Do the same for the values in trial 2, and we get 145.1 centimeter. Get the mean of the computed value for trial 1 and 2, and we'll get 145 centimeters as our probable difference in elevation. And that's it for part 1 of this fieldwork. For part 2, we will use turning points and benchmarks. So benchmarks are either points of established elevations or just reference points with assigned elevation. Turning points are intermediate points between your benchmarks, which provides a temporary point of known elevation for a circuit between two benchmarks, and are used when the second benchmark can't be viewed by the precise level. For example, if the second point is at the summit of the mountain, or if there's an object obstructing the view of the precise level. So the first step is designating your benchmarks. For this fieldwork, we'll be using only two benchmarks, so we'll call them BM1 and BM2. And we'll assign BM1 with an elevation of 0 centimeters. Once done, set up the precise level on a suitable point along the route from BM1 to BM2. Adjust the height of the level to suit the height of the instrument man by using the leg screw of the tripod. And same as before, make sure that the base plate of the level is most nearly parallel to the horizon by doing the steps mentioned in the first part of the fieldwork. Next, take the backside of BM1, where the leveling rod is being held vertical with the aid of a plumb bob. The reading must be done up to an accuracy of a millimeter. So in this case, the reading is 157.5 centimeters. Once again, the recorder should write this down. Next, rotate the telescope until the newly established point to be observed from the instrument can be sighted, and call this your turning point 1 or TP1. Take extra care that the instrument is equidistant between TP1 and BM1. Then, the rod man must transfer the leveling rod at TP1 and must hold it in a vertical position with the aid of the plumb bob again. Take the foresight or FS reading of the leveling rod, and again, the reading must be done up to an accuracy of a millimeter. So in this case, it's 47.5. Next, transfer the instrument in another location along the route to BM2, where the first turning point can be sighted, and then take the reading of the leveling rod. So in this case, the backsight reading on TP1 is 209.5. So now, there are two readings for TP1, one foresight, and now we have a backsight. So just follow the same procedures until you reach BM2. Afterwards, we must close the circuit, meaning you have to repeat the procedure going back to BM1. The elevation that you compute for BM1 must be the same as its given elevation as mentioned earlier, which was 0 centimeters. So the recorded values for the preliminary datasheet should look like this. Next, we must fill in the table using the following computations. So looking at your fieldwork manual, you'll see that the height of the instrument HI is just elevation plus backsight. And elevation is just the height of the instrument minus foresight. To explain, look at the figure here. So once again, backsight and foresight are just the height from the ground to the line of sight of the instrument. And the line of sight of the instrument is just the same as the height of the instrument itself. So if we know the elevation of a point, just add the backsight to get the height of the instrument. Likewise, if we know the height of the instrument, we can just subtract the foresight of the next point to get the elevation of that point. So now let's apply that to our recorded measurements. Starting with BM1, so there's no foresight on BM1, that's why it's crossed out. So all we need is the height of the instrument. So remember, we set the elevation of BM1 to 0. So HI is just 0 plus 157.5, which is just 157.5 centimeters. Next, at TP1, we need to get its elevation first before we can get HI. So elevation is the previous height of the instrument, which is again 157.5, minus the current foresight, which is 47.5. And we'll get 110. Next, get the height of the instrument by adding the elevation to the backside, and now we'll have 308.5 centimeters. So to make things easier, just look at the table. So we always just need to take the elevation first, then the backside. So elevation is always height of the instrument at the previous row minus the foresight of the current row. Then add that to the backside to get the height of the instrument of the current row. Then again subtract that HI by the next FS. And then subtract that height of the instrument by the next foresight, and so on and so forth. And that's it for this fieldwork. So in submitting the preliminary datasheet, just fill out these tables using the data that I will upload in Blackboard. Also, include the sample computation and sketch. The sketch can be a drawing of the different points being measured or a sketch of using the precise level and things like that. So that's it for differential leveling with and without turning points.